The blacksmith's forge is a furnace for heating metals so that they can be worked. If we could magnify this piece of red-hot iron much more than is possible with even the most powerful microscope to thousands upon thousands of times its actual size, we would see its individual molecules darting back and forth at tremendous speeds, far greater than in this animated representation. We do not know what these molecules look like, but according to the kinetic theory of matter, we may visualize the molecules as perfectly elastic spheres. As the iron cools, the speed of the particles or molecules diminishes. In fact, temperature is a measure of this speed. Heat is energy. Heat is energy which may be turned into useful work in a number of ways. Heat drives our steam turbines. Heat drives our tractors. Heat drives our powerful locomotives and the many automobiles on our highways. Heat cooks our food and warms our homes. Heat is the basis of our very existence. When air is forced up through the hot coals of the forge, the oxygen of the air unites with the carbon of the coal. In this chemical reaction, heat is given off. It makes no difference whether the carbon is present in the form of coal, wood, oil, or gasoline. The steam engine, such as this locomotive, is a device for converting heat into mechanical energy. Water is used as the medium. The essential parts of the steam engine are, first, the firebox in which the heat is produced, second, the boiler in which heat is used to produce steam, and third, the cylinder in which the heat carried by the steam is changed into useful mechanical work. Note the sliding valve above the cylinder, which permits spent steam to escape through the exhaust and lets live steam in from the boiler. Steam under pressure comes in from the boiler through the intake valve and forces the piston to move. The energy of motion of the molecules is lost in producing the motion of the piston, and the steam condenses to water. Near the end of the stroke, the sliding valve opens the exhaust on that side and the intake on the other side of the piston. As the new steam comes in, the direction of motion of the piston is reversed. In this way, the energy of motion of the steam molecules is transferred to the piston, and the motion of the piston is used to drive the wheels of the locomotive. The use of steam merely offers a convenient method of getting heat into the cylinder. Here is an ordinary wind wheel. When we let a blast of air strike the vanes of this wheel, it causes the wheel to turn in much the same manner as in the steam turbine. Here, steam is forced into a chamber, and the fast-moving steam molecules strike the curved buckets of a revolving wheel. It is the steam striking these buckets which causes the wheel to turn. The steam then strikes a series of stationary buckets attached to the housing. These change its direction and force the steam against a second rotor, which is also attached to the revolving shaft and adds to the torque. This action of steam may continue through several sets of stators and rotors until the energy of the steam is spent. The steam enters the turbine under pressure, and as this pressure is reduced, the wheels must be larger nearer the exhaust end, since the steam has expanded to occupy more space. such turbines as this find much favor in electric generating plants because they have virtually no vibration, since rotary motion is produced directly rather than reciprocal motion as in the locomotive. The turbine is at the left and the electric generator at the right. When an engine with light weight combined with power is required, the internal combustion engine is commonly used. Quick starting is another feature which makes its use almost universal in automobiles and trucks. The fundamental parts of a gasoline engine are the carburetor, in which gasoline is mixed with air, the cylinder, in which the mixture is exploded, the ignition system, which produces the spark to explode the charge, and the cooling system, operated usually by water. In the four-cycle engine, the downstroke sucks the explosive mixture of air and gas into the cylinder through the intake valve. With the valves closed, this mixture is compressed on the upstroke. Near the top of the stroke, the spark ignites the gas, and the gas molecules drive the piston down to produce power. As the piston rises again, due to the energy of the flywheel, the spent gases are expelled through the exhaust valve. Note that the engine delivers power only on every other downstroke, and that the action may be divided into four parts. The four cycles are intake, compression, explosion, exhaustion. Intake, compression, explosion, exhaustion. In four-cycle engines with several cylinders, the explosion takes place in each cylinder in turn. Thus, each adds its torque to the crankshaft, which, connected through the propeller shaft to the differential gears, causes the wheels to turn. And so, the car is on its way. The diesel engine used in this tractor is similar to the gasoline engine, but lacks both a carburetor and an ignition system. It has a fuel injector. Air is sucked into the cylinder on the downstroke. This is compressed on the upstroke. Therefore, the air in the cylinder rises to a high temperature. At this point, oil is injected and ignites because of the high temperature of the compressed air. The hot gas molecules force the piston down. On the next upstroke, the burned gases are expelled through the exhaust. Note the absent spark plug. The oil ignites spontaneously on injection due to the high temperature caused by the compression of the air. The diesel represented here is a four-cycle engine, but the cycles are different from those in the gasoline engine. They are air intake, compression, oil injection and explosion, exhaustion. All these engines convert heat into work. The oil consumed in this engine produces heat, which in turn does work by plowing this soil. A given amount of heat can always be exchanged for a known amount of work. The first law of thermodynamics states that when heat is transformed into work, the amount of work done is equal to the amount of heat transformed. The second law of thermodynamics says that useful work can be done only when heat at high temperature is changed to heat at a lower temperature.